Welcome to this explainer. Today we're decoding the fascinating roadmap for scaling quantum computers. We're going to take some incredibly dense quantum physics and translate it into a clear, easy-to-follow journey. We'll be looking directly at how the industry actually plans to build the physical highways of the quantum internet, specifically focusing on the cutting-edge hardware and networking strategies being pioneered right now. So if you've ever wondered how we're actually going to move beyond isolated quantum processors, well, you are definitely in the right place.
We've got an awesome path ahead, so here is our roadmap for this explainer. First up, the quantum scaling problem. Then, a really cool analogy for data movement. IonQ's four-stage roadmap, their LightSync acquisition, the massive potential of qubits, and finally, the brutal engineering challenges standing in our way. Let's dive right in. Section 1, the quantum scaling problem.
Okay, so quantum computers are immensely powerful, right? But here's the catch. They face this massive bottleneck because they're effectively trapped in isolation. A single quantum processing unit, or QPU, can really only hold so many qubits before the physics just becomes entirely too difficult to manage in one physical space. To reach their true world-changing potential, these isolated QPUs desperately need a way to talk to each other to form a massive scaled network. But to network these systems, we run into a fundamental physics problem. We literally have to bridge two completely different atomic states. On one side, we have the hyperfine structure. Now, this operates in the microwave range, it has a wonderfully long coherence time, and it's highly reliable. It is the absolute perfect environment for stable quantum calculation. But it is terrible for networking. For networking, we need the fine structure. This operates in the optical range, allows for superfast energy splitting, and interacts beautifully with photons, which is exactly what you need to shoot data down a fiber optic cable. The real trick here is bridging the two.
Section 2, the QPU apartment analogy. To really wrap our heads around how we bridge these computational and networking states, there's this brilliant analogy that compares a QPU to an apartment complex. Imagine your computing is happening in room 601. This is our nice, stable, hyperfine calculation space inside QPU-A. But if your data resident wants to communicate with a whole different building, they can't just jump out the window. They have to pack up and physically move down the hall to a transit lobby in room 602. That lobby represents our fine optical state. Only from there can they actually travel to the next building. Breaking that down step by step, it looks like this. Step 1, we do all our heavy lifting and compute in the hyperfine state. Step 2, we very carefully transition that super fragile quantum information into the fine state so it can hitch a ride on a photon for transit. And then step 3, once it finally arrives at QPD, we have to perfectly remap that exact state back into a new hyperfine calculation room. This physical mapping, from computation to transit and back again, is frankly technically agonizing, but it is absolutely crucial for transferring quantum information. Section 3, IonQ's four-stage roadmap. So, where does IonQ actually stand on making this whole apartment transfer a reality? Well, they've actually already nailed the incredibly difficult first two stages. Stage 1 was getting a single ion and a photon entangled. Stage 2, which they successfully achieved commercially in late 2024, was getting two remote ions to entangle using a photon as a mediator. That is a huge deal. But look at stages 3 and 4. Right now, that entanglement is only happening on highly specialized interconnect qubits. The major hurdles of actually swapping that entanglement over to the working calculation qubits and then scaling the whole process programmatically across a multi-QPU network, those challenges still remain. Section 4, why acquire LightSync? Now, you might be wondering, and it's a great question, if IonQ already proved the core concept of stage 2 entanglement in their own lab, why go out and buy a whole other quantum networking company like LightSync? What exact piece of the puzzle were they missing? In a word, infrastructure. You see, you just can't build a massive real-world network entirely inside a clean research lab. LightSync brings the quantum repeaters, the high-quality quantum memory, and crucial optical chip miniaturization. Lab experiments usually rely on these massive tables totally covered in bulky optics, right? Well, LightSync shrinks all of that down onto tiny chips. Think of it like this. IonQ basically proved they could build an amazing engine. But LightSync, they're bringing the 20-plus patents, the Harvard-trained experts, the highways, and the rest stops. They provide the infrastructure needed to actually drive that car reliably across long distances in a robust commercial network. Section 5, the power of qubits. Okay, let's shift gears from how we move data to how we actually store it, because this completely changes our understanding of quantum capacity.
We've all heard of qubits. They're two-dimensional, existing in a superposition of 0 and 1. But a qubit? That is an n-dimensional quantum state. You can have a 3-dimensional qubit or a 4-dimensional qquart. If a standard qubit is a basic hotel room, upgrading to a qubit is literally like being handed the keys to a multi-story penthouse. It allows for this massive, incredible jump in information density within a single atomic ion. Plus, it gives you way better resistance to errors.
But to make qubits work, we need the exact right physical material. Researchers evaluated several elements for this. Ytterbium is fantastic for long error suppression. Calcium is a solid choice for standard qubits. But barium-137? It completely stands out. Notice how it has two metastable states, and its 5D5/2 state has a lifespan that can reach up to 30 seconds. In the quantum world, 30 seconds is absolutely forever. It offers this perfect balance of long lifespans and complex internal structures that make it the ideal candidate for high-dimensional qubit memory. Check out this truly mind-bending number, 24. Because of barium's unique nuclear spin and electron configuration, its 5D5/2 metastable state has a staggering 24 hyperfine sublevels. Think about what that means. Theoretically, a single barium ion could act as a 24-dimensional quantum memory unit. It blows standard 0 and 1 binary logic completely out of the water.
Now, how do we actually access those 24 levels without accidentally destroying all that fragile quantum data? Well, engineers use this brilliant workaround called the shelving technique. By using highly specific lasers tuned to exact frequencies, they can isolate specific sublevels, literally shelving them in the metastable state. Once they're shelved, engineers can repeatedly read and write to these different dimensions totally independently. It effectively turns a single atom into a highly efficient, multi-partitioned hard drive. In fact, experiments have already successfully demonstrated 13-dimensional and even 25-dimensional qubit operations using these exact principles.
Section 6. Overcoming engineering challenges. So theory is amazing, but taking all this brilliant physics and building it into physical, scalable hardware, that demands absolute perfection. Engineers are facing brutal challenges on a daily basis here. They've got to deal with low photon collection efficiency because it turns out it's incredibly hard to catch a single elusive photon emitted by an ion. They have to maintain strict phase and mode matching across completely different traps, meaning even a microscopic vibration or a tiny temperature change in the room can just instantly ruin the entanglement. Throw in basic destructive photon loss during fiber transit, and the nightmare of trying to squeeze optical components right next to the high-voltage electrodes of an ion trap? Yeah, it's a tall order. But the industry is fighting back and pushing the absolute limits of optical engineering to solve this. They're moving toward integrated photonic grating couplers, literally etching the photon-catching optics right onto the chips for better commercial scaling. For raw lab efficiency, they're using massive high-NA objective lenses. They're also developing some really clever software and protocol solutions, things like time-bit encoding, which makes the quantum entanglement highly resistant to environmental phase noise, and they back that up with real-time phase correction algorithms that automatically adjust for those microscopic vibrations we talked about. And that brings us to the core takeaway of this explainer. Practical quantum memory and photonic interconnects, they are the ultimate bottlenecks in this industry right now. It's really no longer just about building a single processor with a few more qubits. True world-changing scale requires perfect memory and flawless information highways. The company that figures out these engineering marvels first won't just build a better computer, they're going to construct the ultimate quantum network. So, the question we want to leave you with today is, who is going to define the future of the quantum internet?